some cursor is not visible. Maybe it's okay. Let it be.
But you log out. Oh, okay.
It's not muted, right? No, it's not muted.
Okay. Time is up. So today we are very happy to have Professor Sarkar to give us a seminar talk. So Lily is out of duty right now, so I will replace him as the host of this seminar. So Professor Sarkar is our Hong Huan young scientist visiting fellow. So he will stay here for a month, and you can visit him in office in this building anytime you want it. So let me make a brief introduction to Professor Sarkar. Professor Sarkar is a professor of physics at the Indian Institute of Technology at Gandhinagar in India. He obtained his PhD from the Inter-University Center for the Astronomy and Astrophysics in Pune, and subsequently conduct postdoctoral research at the University of Maryland in the US. And his research interests lie primarily in gravitation, gravitational wave, and black hole physics. So today he will give us a talk about beyond Einstein and assessments of higher curvature gravity. Okay, let's welcome.
Okay, first of all, let me thank all of you for this wonderful hospitality. I'm really enjoying the great food here, and also,
yes, maybe you can speak to this computer, otherwise.
Yeah, I'm really enjoying. Yeah, I'm really enjoying my stay here. Thankfully, the weather is also quite good. Okay, at least for my standard. Okay, so what I'm going to talk about is this idea that it's an old idea that one could go beyond Einstein's theory of gravity, add higher curvature terms. I'll try to be slow, so please stop me whenever you want me to stop. So as Shao has told you that I work at IIT, and IIT stands for Indian Institute of Technology. This started with engineering institutes where people
you can continue.
Okay. So this started with engineering institute, but slowly then we're grown up with a science program and science department. So they are relatively well funded places in. You want to mute?
Yes, it's
participants. You can mute everyone.
Only I can mute here.
You can,
yeah,
you are the boss.
I will mute from there. Sorry.
Fine. Okay. So let me go back. So they started with a physics program, and now every IIT, now there are 23 IITs all over the India, and hopefully some will more come. They're relatively well-funded places in India, where the government has put a lot of money for science and education. Okay, so all of you have, I'm sure, have read this book, Landau and Lifshitz, Classical Theory of Field. I mean, it's a standard textbook all over the world in many subjects, in foundational subjects in physics. So if you look at classical theory of field, the last chapter discusses gravitation, the classical theory of gravity, particularly general relativity. And if you know this book, Landau and Lifshitz, that these books are classics. I mean, in a sense, they're very dry books. Okay, they don't discuss anything other than pure physics. Okay, but even in that book, there is a line which you will find which contains no physics. It's very difficult to find a line in Landau and Lifshitz which does not contain physics. Here's this line which says the theory of gravitational field constructed on the basis of theory of relativity is called general theory of relativity. It was established by Einstein and is finally formulated by him in 1916 and represent probably the most beautiful of all existing physical theories. This is very unlikely of the other things written. It comes with a very high emotions, okay? And if you know how Russian schools, how serious they are, okay, it's a very, not a very characteristic line in a books like Landau. So it shows that even they are very impressed by the beauty of general relativity. And there is no doubt that general relativity remains a cornerstone of human achievement, what man can, and man and woman can achieve together in the field of thinking. So the general relativity, of course, supported by every observational test we have done so far. Okay, so all observation tests are consistent with general relativity. And so there are many tests, like classical tests, which all of you know in your textbook. But I'm going to mention this. This is important. According to general relativity, a binary star system could radiate energy in the form of gravitational waves. So two stars coming close together, they will, form a binary system, and then they will come closer to each other by losing angular momentum and energy. And then part of the energy will be radiated to gravitational waves, and part of it which you can detect here. And the interesting thing is that since they are radiating energy, you can measure the change in the period of the system. The period will generally decrease. This was known even to Einstein, who first derived the quadrupole formula, because he also realized that the radiation will start with the quadrupole. There is no dipole component of the radiation because of the angular momentum conservations. And if you can measure the period of the system accurately, which is true for pulsars, we will be able to understand exactly the change of the period. And therefore, we'll be able to, verify the predictions of general relativity. So there is a very interesting formula. This is not the original quadrupole formula. This is formula by Peter and Matthews, 1963, much later. But this contains all the corrections due to eccentricity of the orbits. And this is up to the quadrupole level. If you know this, g to the power 5 by 3 by c to the power 5, this is up to the quadrupole order. Okay. And this is for two masses, and M1 and M2, and this is P dot, which is the change in the orbital period. Okay. So each time you go for one is a one period. And if you wait for years and years and observe this, you will see a change in the period. Period is decreasing. That means energy is being coming out. It's a dissipative system. Now, why this test is important? Because if you go and read the history of general relativity, there are a lot of debates on the derivations of this formula. There are conceptual debates, and there are even calculational mistakes, even by Einstein, by some factors of pi and 4 pi. Okay. So particularly when this formula was first, confirmed by observation. So this is the recent data analysis of this gravitational wave for the period observation from this famous Hall-Stellar binary pulsar, and you can see the decrease in the period over the time. And this is the observational data, and the solid line is the predictions for general relativity. Look at the error bars. It's profound, actually. So this formula has so many debates. Okay, people thought, okay, maybe this calculation is not valid. Maybe we cannot use the post-Newtonian formalism near the binary system. So many things. But this is what everybody will agree. There is nothing you can do after this beautiful thing. It is clear that general relativity can be verified, and it works exceptionally well. Okay. And this is something which is the reason why you would call it a beautiful theory. So let us go more into the physics of general relativity, which all of you know probably better than me. So we have special relativity, that is physics without gravity. So where the space-time is given by Minkowski line element. So neither the space nor the time is absolute, but the space-time, which I call the light pulse structure, is absolute in special relativity. It does not change. Once you have given the metric, you know whether two intervals are time-like separated or space-like separated or null separated. They are fixed for all. Now, what general relativity says that in the presence of matter and energy, the gravity is there is a gravity, and then the space-time is no longer this line element, but rather a general pseudo-Riemannian manifold equipped with a metric. Generally, we assume the metric has zero torsion, metric compatible, and all simplifying assumptions. But you could do more general here. And in that case, this metric is now can change, can fluctuate, the light cones can tilt and flip, You can come up with crazy examples when there's a closed time-like curve, if you want, such as spacetime, whether they're physical or not, it's a separate issue. So, for example, when there's a collapsing matter, event horizon forms, the light cones come closer and they can tilt, and you can even have null surfaces from which you can only enter, you cannot come out. So, all these things are known. So, there is this dictum in general relativity, which is because of Wheeler, which says that matter tells spacetime how to curve, and curved spacetime tells matter how to move. This is something which we have learned in our basic GR books. So, in a curved geometry, test matter moves on geodesic curves, a generalized notion of straight lines on place. So, this is something called. Now, the question is, what is the dynamics of gravity? What determines the gravity itself, the matrix itself? And the answer is, of course, the Einstein-Hilbert tensor, Einstein-Hilbert action, which in the presence of the cosmological constants takes this form, where R is, of course, the Ricci scalar. And if you vary with respect to that metric, having right amount of boundary terms and taking care of all the issues, you would have got the famous Einstein, which is nothing but geometry and matter equivalence. Okay, this is. I might like to emphasize that look at this curvature R, okay, the Ricci scalar, which itself contains the second derivative of the wave, because that's the simplest scalar you can make out. So already this action is a little weird compared to your field theory action. There is no del phi structure in this matrix, because it already contains the second derivative. Although it contains the second derivative, when you vary, you don't get a higher order differential equation. You still get a second order differential. Now that is because of very special structure of this term and the structure of the boundary term. This is known. And also the Einstein-Hilbert action is the simplest choice. We could have chosen something else. Action is always a guess, but nevertheless it works very nicely. I would also like to emphasize that, of course, I have set C equal to 1, but note that in Einstein gravity, there is no other coupling constants or dimensional parameter except two, Newton's constant and speed of light c. That's all what you have. Okay, there is no other dimensional constant. So let's go ahead. Of course, there is no reason to stop at Einstein gravity. If you want to make your life complicated, you can add more general terms. For example, if you believe that you want to add only isomorphism invariant terms, you can go ahead and terms like RNA, RNA-CD, and whatever. All kind of scalars you can constant. For example, you could. Sorry, it's okay. So, for example, you could add a new Lagrangian, which is of this form. Okay. So once you add it, because of dimensional reason, now you have to add new coefficients, alpha, beta, and gamma. I can keep it arbitrary. Okay. Note that all this coefficient comes with dimensions and appropriate dimensions of length or mass. Okay. So remember. All this coefficient. Now, what are the motivations of adding such coefficients? Okay, of course, the motivation is very relative term, but you can still come up with some motivations with others, right? For example, I know that general relativity is a non-renormalizable theory. Perturbatively, general relativity cannot be renormalized, just like what you can do with QED, you cannot do with gravity. Nevertheless, because it's a non-renormalizable theory, it will make sense only as a low-energy effective theory. In effective theory, you can always add higher dimensional operators, an infinite series of higher dimensional operators. In gravity terms, they are nothing but higher curvature terms. Okay. For example, if you look at this famous two-loop divergence in perturbative quantum gravity, this is how people established the renormalizability of gravity in 16 and 17. You come up with a term which cannot be absorbed in any redefinitions of the Newton's constant and cosmological constant. See, the idea is that if the gravity is renormalizable, you will always be able to absorb all the infinities, loop infinities, into redefinitions of your Newton's constant, or maybe the cosmological constant. But what Proust and Wettman showed that that cannot be done. In fact, later other people also showed that cannot be done, and there will be this term which cannot be absorbed. This is formally a divergent term, cannot be absorbed into redefinitions of the coupling constant. Therefore, the gravity two-loop gravity with matter will be definitely a non-renormalizable theory. You require infinite number of coupling constant at every order. Okay, it doesn't have any predictive power. So therefore, maybe by adding this higher curvature term, you could have made the UV behavior a little bit better. That was also one of the old motivation for this stuff. And of course, everything can be motivated from string theory, and we know that in string theory there are alpha prime corrections in string actions, and then alpha prime can be anything. Okay, there is no reason for alpha prime to be at the Planck state. And also, if you're interested in new physics, you know that these terms will change the Einstein's equations. There will be very rich phenomenology. There will be new solutions, which was not there in Einstein gravity. Not only that, there could be solutions which have no Einstein branch, because they will lead to, in general, higher derivative equations. They may not have anything which connects to general relativity. So it itself is a very interesting thing to study, that what are the properties of these terms, what are the solutions, what are the space of solutions, what are the new properties, how black hole thermodynamics changes. So therefore, these terms have been attracted to a lot of attention.
Question.
Yes.
Yeah. Here you mentioned this is a pure projective quantum gravity effect. So my question is that is the low energy effective action of string theory necessarily involving a scalar field?
Involving?
A scalar field.
Dilaton must be there, right?
So there must be a.
There must be a dilaton there.
Okay.
But the question is that the places where we could able to calculate, let's say we have this heterotic string theory, where up to a compactification we could able to calculate the form of the high curvature corrections. Or type 2 string theory, where there are a lot of supersymmetry, you can calculate things. You can calculate up to certain order the form of the higher curvature terms. Type 2 string theory, the higher curvature terms start at the cubic order in curve, sorry, R to the power 4. Okay, because of the supersymmetry, terms cancels out at the lower order.
So the non-minimum coupling is unavoidable.
I think if you work from the string theory modification, you not only get the higher curvature term, you get all possible host of coupling. There is no doubt.
Okay.
So if you actually want to write down the proper string theory effective action, you have to take into account all the fields you also get. Like you will not only get scalar field, you will get some kind of F mu fields also. And you will get non-minimal coupling as you are talking about. So in general, the actual actions will be much more complicated than what the simple things. Absolutely. So let's go ahead. So as I was talking to you, that the inclusion of such terms leads to new phenomenological constant like alpha, beta, and gamma with appropriate power of length. Okay. Now, immediately the inclusion of these terms led to the modification of general relativity at scale determined by this dimensional constant. Now, you may say, what is the length scale which describes the new physics? Of course, we have our length scale, which is Planck scale. But if you set things at Planck scale, then, I mean, what are you doing? I mean, you can't do any classical physics with such scales. Okay, so the expectation is that there is some scale, let's say at alpha, beta, and gamma, where I will be able to completely ignore the quantum fluctuations. I'll be able to treat gravity classically. Nevertheless, this terms will contribute. This is an expectation, there is no proof. Okay. But in the effective field theory sense, we assume that there will be some new scales at which the quantum fluctuations can be ignored. I don't have to do quantum gravity, but I will be able to do classical gravity with this new terms. So that's the expectation one should make. In that sense, one would like to use observations to find constraints on this new coupling. So the fact that we have not observed this coupling immediately tells us that how far that scale should be. What is the upper limit of this scale? Okay. And what are the observations you can do? You can do many observations, whatever you like, but these are the three things which I like to mention. Whenever you add these terms, you let the modification of the inverse square force law. And there are very precise experiments you can do in the lab. Newton's law, Newtonian potential will be modified, and you can do experiment in the lab to put constraints on this term. The gravitational wave observations will be modified because Einstein's equations are modified, and there may be new features, new interesting features. The space of black hole solutions will be different, the symmetries of the solutions will be different, constraint. And there is also cosmological observation in early universe. You could find out constraints on this stuff, and all this have been started almost beating to death. There are like thousands and thousands of papers. But you don't have to do much complicated. Okay, you can immediately put a constraint. You say that, okay, the contribution here, just at an order of magnitude, let's look at this action. The order of magnitude is alpha r square, and gr is r. The fact that I have not seen anything other than gr tells us my alpha should be such that alpha r square much smaller than r. It has to be, it's like almost automatic. Okay. If you do that, immediately you say that alpha must be much less than the length scale at which I can do my observation. The minimum length scale where I have been. So what is the minimum length scale? I have probed the gravity. If you are doing gravitational wave observations with a black hole, let's say a Schwarzschild radius. What is a Schwarzschild radius? Let's say a few kilometers of a black hole. A medium-sized black hole will have an order of magnitude of 10 kilometers Schwarzschild radius. That immediately tells us, at least by simple magnitude order of magnitude, alpha must be much less than a kilometer length scale. For the fact that I have not seen any higher corrections to my gravitational wave. You could do more particularly complicated corrections. So there is a paper by Perkins and Nicules which that took a particular solutions of Einstein high curvature gravity, did full inspiral waveform analysis, and figured it out the constraint. But at the end of the constraint says this, okay, which you would have guessed even from order of magnitude calculation. But it's important to do this calculation so that there is no surprise. Okay, this is a standard. You can also do torsion balance kind of experiments. Okay, because once you add this term, I told you that there will be change in the Newton's law. And again, closer you can go to 2 points and study the Newtonian potential, you will get better and better constraint. So, in this kind of experiment, you can actually get a very high constraint. But what the problem with this is that here you are only changing the phenomenological change of the Newton's law. There could be many other effects. For example, what if graviton has a finite mass? It will change the force law to Gauss force law. Okay. So from here to going into higher curvature terms is not that easy. It's very theory agnostic form. We get around by using when the first gravitational wave observations of a time delay came. So for example, when the light comes from gravitational wave observations of two neurons turn collapse, the gravitational wave also comes, there is a slight delay of few seconds. Now, if you say that I ignore all astrophysical contribution to that delay, I want to know what is the upper limit on the higher curvature terms for which there will be a delay. So this is an upper limit because I am ignoring the astrophysical reasons for a delay. Please understand the limitation of that. Then you get some constraint. But if you see this constraint, first of all, you will notice that observation constraints are weak because however you think, actually, most of the black holes very close to the horizon, if you calculate GM by C square R, it's not very high. Okay. It's not easy to probe strong gravity. So therefore, still I would say that experimental constraints or observational constraints are not very strong on these terms, except this kind of experiment. But there is no reason to feel bad. Apart from we are, at least I am theorist. Most of you probably are theorists. This is the Institute of Theoretical Physics. So we can go beyond observational constraint. We can also put important bound on this higher curvature terms using theoretical and physical constraints. So that we can. Maybe we can do better than sometimes to the observer. That will be really great. For example, general relativity is a robust example of a well-behaved theory. What do I mean by well-behaved? It has all the properties we want from a theory. As an example, let's say it's very difficult to define local energy in general relativity. Like there is no notion of local energy of gravitational field. So you define a global energy like ADM mass. Now, if you look at the expression of ADM mass, I am sure you must have wondered what is the guarantee that ADM mass will always be positive for a reasonable space. But we know there is a remarkable theorem by Witten and later by Yau and others that there is a Witten's proof came later before the mathematicians' proof of the positive mass theorem. And the positive mass theorem ensure that the ADM mass is positive, ensuring the stability of fat space because Minkowski space has zero ADM mass. So that's remarkable that the general relativity has such nice properties. Okay. So the question you could ask that does any diffeomorphism invariant theory, is the diffeomorphism invariant theory is a sufficient criteria to obtain consistent gravitational theory? It may or may not be. Maybe it is Einstein gravity which has all these properties. Once you go with Einstein gravity, things are crazy, things are bad, and then you should not consider those theories as viable physical model. But then you have to define what are those consistency criteria, and most of the fight comes from here because my consistency criteria may not be your consistency criteria. But there are certain almost agreed upon universal consistency criteria. For example, causality, ghosts, tachyons. You don't want theory to have ghosts and tachyons. The fluctuations of that theory, if it has ghosts and tachyons, you don't like those theories. You want positivity of energy. You want black hole mechanics. For example, in general relativity, of course, there is no proof of cosmic censorship, but it's very difficult to come up with a counterexample. You don't want a theory where a counterexample to cosmic censorship is almost trivial. Such a theory will be bad to what? So these are the consistency criteria you can impose on a theory and come up with the set of theories which you like. Let's say in general relativity, if you linearize the theory about background, you will get two physical modes of polarization. This is well known. These are Maslow's graviton propagating over flat spacetime. Okay. Now, if you take this theory and do the same calculation, you get the following structure. You get a massless graviton, two helicity massless graviton. You also get a massive scalar mode, and you also get a massive graviton mode. And these modes have mass inversely proportional to this couplings. So couplings goes to zero, this masses goes to infinite, so they become completely decoupled from the theory. This is a standard linearized gravity calculation for this theory. Now, the problem is that these masses are not guaranteed to be real. The expressions for the masses you get, there is no guarantee that for all values of alpha, beta, and gamma, these masses are real. So therefore, if m square or mt square is negative, you have what is called the tachyons, imaginary mass, and then that's a very bad theory. So it turns out there is a constraint in d dimension that alpha, beta, and gammas have to obey this particular constraint to make non-tachyonic condition. Otherwise, your theory will have tachyons. So you may say, okay, I will only work on this particular regime. Okay, I don't know why, there must be a physical way of understanding, but maybe my UV physics will give a rationale of working in this particular regime, parameter space of alpha. Okay. In four dimensions, this will reduce to this relationship. But that's not good enough. You may get rid of the tachyon, you will still have ghosts. Okay. By ghost, what I mean, these theories in general will give higher curvature, the higher derivative equations. Okay. So if you look at higher derivative equations, for example, your Lagrangian, generally your Lagrangian is of this form, where it's a function of q and q dot. But if your Lagrangian contains q double dot, you will get this kind of modified Lagrangian equation. And it's a fourth order differential equation, and therefore phase space is 4-dimensional. So you have to be careful in defining what is the Hamiltonian. Okay. And this is done by Ostrowski. So if you define the Hamiltonian to be a generator of time translation, it turns out in this 4-dimensional phase space of this kind of theories, Hamiltonian would be like this, and there will always be a linear term. You cannot get rid of this thing. That's a theorem by Ostrowski. Okay. I don't know, there are many good references of Ostrowski theorem, but I forgot to add reference. This is classical mechanics. If there is a linear term, it means there is always a region in the phase space for which, because momentum can have any sign, the Hamiltonian is unbounded from there, which says the theory, free theory, if you add perturbations, will be totally unstable. So this is what is called the Ostrowski instability in classical mechanics. Any theory for which the equations motions is higher order differential equations will have this Ostrowski theory. Thankfully, my Newton's laws are second order, so therefore we don't have Ostrowski instability in classical mechanics. Okay? So higher curvature theories in general will have this. So even if you can get rid of tachyons by appropriate only, saying that I will only work in this parameter space, we will always have any parameters. In fact, you can show that unless alpha, beta, gammas are 0, you will never get rid of the force. Okay. In fact, you can come up with certain very special class of theories, but in general, they will always have. They are very problematic. So you ask that is there a model of theory for which there is no such problem, no tachyons, no ghost? And that answer is given first by Lovelock in 1976. It's an old theorem. If you are interested in new proof, look at this Edison papers in 2022, where there is a very interesting new proof. What it shows is that, unfortunately or fortunately, in 4 dimensions, there is only one such thing. That is Young gravity. At least as long as metric is the only dynamical degree of. Apart from general relativity, in 4 dimensions, you add any term, you cannot get a second order differential equation. But if you want to go beyond general 4 dimensions, which if you want, okay, then of course you will have a class of theories, what is called the Lovelock-Runge gravity. Okay. And for example, d equal to 5, the unique model is this. There is nothing else. For which you have to add the specific combinations of terms with this appropriate coupling constant. And this is what is well known as Einstein-Hilbert gravity. If you go in higher dimension, you can add more and more terms. They are related to the Euler densities of this particular dimension. And this theory is guaranteed that you will get a second order differential equation in time, and therefore there is no perturbative ghost as well as tachyons. This is like as good as zero relativity, but only is finite. So this seems like a good theoretical model to understand the dynamics of higher curvature theories. They are necessarily higher dimensional, but they admit nice solutions. So therefore, a lot of people have spent a lot of time on this case, understanding the dynamics of this case. But then come back surface. So there is this paper by Kamano, Edison, Madasina, and Yuganov, this I will call some CEMZ in 2014, where they claim that such a well-behaved theory, which generally general relativists like, okay, Lovelock gravities or Einstein-Hilbert gravity, also has a possible subgroup. And it violates what they call causality constraint. So I have to explain what is their causality constraint. Okay. So before I go explanation, just give you a head up. So this constraint, terms causality constraint, was identified through the analysis of what is called a Shapiro time delay phenomenon. Okay, which is basically the change in the travel time of signals, both time-like and null signal, in the presence of mass and energy. In a sense, the phenomenon refers to the slowing down of the light signal near a gravitating body. And then these papers conducted their analysis by observing a Shapiro time delay of a gravitational wave interacting with a top-wave solution within this theory. Why they are doing it, I will explain. But the main point is that if this Shapiro time delay has a particular sign, for example, if the Shapiro time delay has positive sign, the theory makes sense. It's like sign of this Wilsonian coefficients of scalar effective field. So any theory they claim for which this Shapiro time delay is positive definite in a particular convention, such theory makes sense. And they show general relativity belongs to that class of theories, for which the Shapiro time delay is always positive. In fact, they show that in Einstein-Hilbert gravity, Shapiro time delay can have negative sign for either sign of the coefficient alpha. Okay, and that's very disturbing. And then they show that there is this theory violates causality in a very precise sense, which I will talk about, but Gao and Wald proposed. So basically, what they show that this kind of theories, which seems to be very well behaved theories, Shapiro time delay can have negative signs. And then you can use the negative sign to create what is called superluminal propagation without violating an energy condition. That's important. Because even in general relativity, you have closed time-like solutions. Okay? So, and therefore, this is incompatible with the consistent classical theory of time. So their claim is that the theory which we consider to be a well-behaved theory is not a good theory. It has causality problems. And then this paper is like everybody's enemy because relativists never liked it. And string theory says that therefore there is nothing other than the high curvature gravity has no physical meaning. Good. Let's go ahead. So let us understand what is the claim. Okay, so I'll be brief. There are a lot of technical issues, but I'll try to give you the gist of this. Okay. So if you understand the CEMZ result, you have to start with this very famous paper by Tooth. It's called Gravitational Dominance in Ultra-High-Energy Scattering. So this is a very famous paper where Tooth shows that if you go to very high energies, in a particular limit of scattering, nothing dominates other than the gravity. You can ignore all effects of the standard model. But this is sometimes it's called the gravity dominance in the high energy scattering. So in certain, that is simply because if you look at the Mandelstam variable, the scaling of the scattering amplitude with respect to the Mandelstam variable, for gravity, when S by T, S square by T is very, very high, it is the gravitational exchange which always dominates. The scalar field or the standard model field cannot catch. So Tooth shows that therefore, if I have a scattering amplitude process of two time-like particles at CM energy order of Planck's units and beyond, you don't have to do actually quantum gravity. Even using classical gravity regime result, you will be able to give you an exact value of the scattering amplitude. And then Tooth actually evaluated this amplitude by solving Klein-Gordon equation of one particle in the gravitational shockwave of the other particle. So basically, you are looking at scattering amplitude calculation. If it is a very high energy scattering amplitude, you can forget about quantum field theory. Tooth shows that three-level result is equivalent to a shockwave solution of general relativity and the particle moving in that shockwave. So instead of solving the quantum gravity result, the three-level result can be obtained by looking at shockwave solutions and a point particle moving in that shockwave solution. Three-level, that is why you can. Okay.
Sorry, what do you mean by the shockwave?
I'll explain what is a shockwave relativity. That's a good point. And later, other people showed that same result can be obtained, what is called econal approximation. This approximation basically means S square by T much greater than 1. Momentum in the S channel is much higher compared to the momentum of the T channel. So I have to explain what is the shockwave. So before I go, I'll just give you the result, then I'll go to the what is the shockwave. So basically, in that limit, one could show that the scattering amplitude will be given by this form. This form is 2 scattering. Okay. And these are external legs of momentums. U and V are the light-like directions. And this formula gives you a phase e to the power delta, which is of this form, where B is nothing but the impact factor of one of the particles. So this is a shockwave. I'll explain what is shockwave. So that has an impact factor B, and this B is the impact factor. Okay. So this is the case for general relativity, and they show that the same result can be obtained by using a classical observable by time delay shockwave geometry. Before I go, what is the shockwave? Note that it is quite clear this delta is positive. This is the calculations in gravity, general relativity, when the linearized Einstein equations are.
Yeah,
Now,
but it also diverges if we equal 4. So what's the problem?
Can you read?
It diverges at the 4 dimension, right?
Yeah.
Very good point. Okay, so this result explicitly assumes that D is greater than 4. And I'll explain why D is greater than 4. Actually, what happens is that the time delay has a logarithmic branch at D equal to 4. Well, since you have a log, this is well known in the Axelberg tooth metric also. Since D equal to 4 is logarithm, you need a IR cutoff explicitly to get rid of this log B by something. So therefore, one has to be very careful in a gauge invariant way of talking about time delay. They want to avoid that problem and go to the higher dimensions to do this calculation. Lower dimension, you can do these calculations, but you have to be a little careful about how to define the things independent of the IR cutoff. I have not just mentioned that. Good.
Now, what is the shock wave? So think of you're solving Einstein's equations with a source. What is your source? A particle moving. It has energy and momentum. It's your energy momentum tensor. You can give it to right hand side of the Einstein's equation and solve for the metric for that. Now assume that particle is moving at the speed of light. Okay. So then what you have is called a shock wave. And you can solve Einstein's equation with shock wave energy momentum tensor. And this is known in Axelberg and Schatz and Tubes. A lot of people have solved it. So the energy momentum tensor is given by this form, but U component only exists, and U is the one of the light-like direction. Since it's a single particle, the entire energy momentum tensor is concentrated on delta U. It's a delta function at U. Since it's moving on at the speed of light. Okay. And it's a particle. You can put it into the space-time, solve Einstein's equation, and this is first proven by Tufts and Gray in 1980 that the solution metric would look like this. It has UV component because it's a space-time for a null particle with this particular property. It's a distributional solution because there is a delta U there. Okay. That is because you are solving for a distributional source.
Okay, so what was the comma there?
What was?
Comma.
The comma. What I mean.
Oh, sorry, this comma is a thank you, sorry.
Oh, okay.
Sorry, my because I copied it from the it's entirely mine. And these are the transverse directions. Okay. So there is a UV directions, and these are the d minus 2 dimensional transverse direction. Good. So what is happening? So this is a flat space-time kind of space. Now there is a shock wave which is moving in this direction around U equal to 0. It's moving in grid. Okay. Now you shoot a particle. The particle is moving in some v. This PV has this moment. So it does not touch the shock wave. Don't confuse yourself by looking at this picture because this picture is only at a two-dimensional thing. There is a separation in the transverse direction. So there is an impact parameter V. So this is a shock wave. This guy comes from here. There is a impact parameter V, and then it goes back. Okay. So it is going like this. Okay. So in this picture, in Penrose's diagram, I cannot show you the other transverse direction. So it looks like that it is touched. Okay. So what is happening is that a particle comes, another takes a graviton, goes to the shock waves and comes out from here. Okay. So what does this represent, this distance? It represents a change in the affine parameter time. This is your Shapiro time. Okay. So what is happening is that either you are getting advance in time by the gravity, or you are getting backward in time by gravity. So gravity, you are changing your notion of time. If you move, there is a time delay or time advancement, just like it happens for signals which are at two different gravitational potential. When you come close to the, this is actually observed in solar system test, okay, but not for light, okay, for planets. And then in general relativity, you can show that shift is, if you solve the perturbation equation, is given by this formula, and it is manifestly positive. What Cavart and they show is that using Tufts result, that this scattering amplitude delta is exactly equal to this shift delta. This is what they have to do. So the idea is that suppose you are doing in this calculation in some crazy theory of your own, and you get delta V to be negative or some other sign. Okay. That will immediately tell that 2-2 graviton scattering, high energy limit of the 2-2 graviton scattering, the phase delta will have a different sign. Now, sign in delta is very important because if you remember your optical currents in results in quantum field theory, the phase has to have a specific sign if you demand unitarity. So basically, by showing one-to-one correspondence between delta V and the phase, Cavart show gives you a diagnostic tool. If any theory delta V has a wrong sign, your theory will have a problem with the unitarity. Now, note that this shock wave is just a calculational device. It just tells you, without calculating this amplitude, okay, in quantum field theory, can you calculate in the classical gravity? Which is what Tufts has shown us how to do that. So the shock wave for example, sometimes people say, okay, what if I don't consider a shock wave? I consider some physical particle. You can do that Shapiro time delay calculation, but that has no meaning in the language of the quantum physics. This correspondence between phase and the shock wave time delay exists only way your source is a delta function. So this delta function is no physical thing. It's just a a device to calculate that delta. That's all. Okay. So instead of doing calculations in field theory, you are calculating a the process of graviton passing to the shock wave, you can map everything as a signal process problem. So there is something F out and there is something F in and there is an amplitude SW. Okay. And then with the mass shell condition omega equal to PV for that particular one. Now, if you demand causality in such a process, you know the S matrix element for graviton going into graviton, call it some SGGW, must be smaller than the one of the upper half plane. This is the condition that you go to the upper Argand plane, SGG must be less than 1, otherwise you will have problem with the unitarity. Now, what happens? So think so basically this magnitude must be less than equal to 1 for imaginary omega greater than 0. This is the condition for causality unitarity condition. Now what happens is that if you look at, since you are looking at only in the what is called the equal limit, you can only look at the infinitesimal value of this SGG, and you can show that calculations will give you that the relationship between SGG and delta V is of this form. SGG equal to 1 plus I delta V into omega. Okay. Now, imaginary omega is positive. Now think of that if your omega is negative and if your delta V is negative and if your omega is the upper Argand plane, let's say I into something, okay, the plus I, remember it's the upper Argand plane, then SGG will be greater than that. Let me again explain. The infinitesimal SGG for this kind of process will be given by this formula, where delta V is the scattering, the Shapiro time delay. Now, if the Shapiro time delay is negative, omega is some positive number into I, because it's in the upper Argand plane. I into I is -1, delta V is again negative, it gives you +1 plus something. Immediately that get rid of this question. So that is why a sign of delta V is extremely important. Without the sign of delta V, so for example in GR you can show delta V is always positive, unless you are crazy enough to work with, let's say, negative Newton's constant. Okay. So therefore, there is no way you can violate causality in GR. That's the rule. So in GR, as I said, delta V is manifestly positive. There is no causality issue in the sense of C embedded in GR. Now, what will happen if there is a negative Shapiro delay? For example, I show that causality will, unitarity causality will be in problem. Not only that, the CMs will also show that if you have a negative time delay, then you can construct a closed null curve without violating an energy condition by using two shock waves. So you go from one shock wave, come back in a previous time, enter into other shock waves, come back in earlier time. So you can create a closed null curve. And they said this is also very bad because you are not violating any energy condition, creating a closed causal curve. By the way, I will not tell you to take this very seriously, because there is a very interesting paper by Arvelia and Paolo where they showed that this kind of construction is indeed possible as a sense of this theory, but there is no initial value, a consistent initial value or initial data from which you can evolve and get into this configuration. So these configurations are unattainable by generic initial data, consistent initial data. So therefore, they cannot be constructed out of physical initial data. So this kind of problem need not be that serious. But this problem doesn't exist. So this is the paper where they show that how to construct this machine, and they show that if you want any generic data from which this machine is constructed by evolving against the Gauss-Bonnet equations, you necessarily have portion of the Cauchy surface which is not spaced. That means your initial data formalism is not very well. So they are there, but you cannot construct. So, but there is an exact theorem also by Wald and Gao that in GR, as long as null energy condition holds true and time-like conformal boundary can be attached to the space-time, which you can do for most of the solution, such a space-time with boundary satisfies what is called strong causality. And basically, any first-case null geodesic connecting 2 points in the boundary must lie entirely on the boundary. So basically, what it says that you cannot self-signal then what is allowed by the asymptotic causal structure of the space-time. So this is a theorem you can prove in general relativity. So in fact, what CEMnet shows that if your probe graviton suffers a time advancement, that it may be possible to send a signal by 2 detectors at infinity faster in the bulk than asymptotically. So therefore, you will violate the Boyd-Bow criteria of causality. But I myself do not consider this as a serious problem because this Wald and Gauss conditions is proven by using Einstein's equations. So in a high derivative gravity, when Einstein's equation is not true, I don't even know what does this violation mean. Okay, so I will not go into very seriously into this, but I should mention what happened. So where is this negative sign coming in a theory which is not GR? Okay, that also is shown by Shi. Then what they show is that suppose you are looking at expansion in HT waves. Okay, so you have 2-point coupling, you have 3-point coupling, 4-point coupling, okay, in a scattering cross section. So what they show that this Shapiro time delay is entirely coming from 3-point graviton coupling. So basically any theory for which a 3-point graviton coupling is different from GR can have issues with the Shapiro time delay. So the question is that any higher curvature term which modifies the 3-point graviton coupling will have a causality issue, and in the sense of CEMnet. This is the assertions they give. Okay. That you add higher curvature terms, it modifies 3-point coupling. Those 3-point couplings change the sign of the Shapiro time delay, and then that leads to the problem in the causality of 2 to scatter. Okay. That's the sense of logic. And they give an example of 5D Gauss-Bonnet theory. Sorry. 5D Gauss-Bonnet theory. What it turns out, even for Gauss-Bonnet gravity, the GR solution remains a solution. Okay. So therefore, the Shockel solution is also a solution for Einstein-Gauss-Bonnet gravity. So you take the GR solution, but now you look at the graviton perturbation in that GR solution. Now the graviton perturbation equations is different. In GR, you have to set lambda to 0. Lambda is like alpha into some factor. Okay. So they leave that. Okay. And then they calculated the Shapiro time delay, and then show that there is an extra term. And what are these epsilons? These epsilons are the polarization dependent term. Now different polarizations have different Shapiro time delay. In GR, all polarizations have universal time delay. Okay. But now different polarizations have different time. And then they show you can choose any sign of this coupling, but you can always choose physical polarizations for which you can make the sign reverse. From positive, you can make it negative by choosing a different polarization because of this minus sign. So it is possible to find polarization, physical polarization, what is allowed, such that the time delay can be made both positive or negative sign. This is a concrete example they show that Einstein-Gauss-Bonnet gravity delta V will be negative. Not only that, they show that this negative sign is coming because Einstein-Gauss-Bonnet gravity has a different shock 3-point coupling. They also show theories with non-minimal coupling also may have this kind of property. Okay. Anyway. So it is important to appreciate that couplings has to be order 1 in terms of impact parameter B. Otherwise, this problem does not come. For example, if you say my couplings are of a Planck scale, there's absolutely no problem because you are doing a semi-classical analysis. Okay, you're doing a semi-classical, rather classical analysis. So therefore, this problem comes as long as the couplings are order 1. So you are saying that does the Gauss-Bonnet gravity make sense as a standalone theory of extension of general relativity? The answer is, according to CEM, that is no. And in fact, they show that if you can, it cannot be compensated by adding new massive particles to your theory. In fact, there is a proof that infinite tower of massive particle, as long as these particles are not ghosts. Okay, that means their kinetic terms have usual sign. Then you cannot solve this problem unless you add an infinite tower. I'm not going into that proof. That proof is a bit complicated. And then they indicated that this seems like a string theory. So a theory with infinite amount of tower of massive particles seems to be like string theory. So the conjecture is that, not a conjecture, it's a kind of reasonable argument. Either GR or an infinite number of terms with infinite towers of particles are consistent in terms of causality. Nothing else in between. So the claim is that either you choose this guy or this guy. There is nothing in between. Okay. But what we found that there is an implicit assumption in the formulation of CEMZ. Okay. The implicit assumption is that they do not consider the possibility of ghosts. Of course, you should come and catch me that ghost itself is a bad. For the time being, allow me to have ghost in my room. Okay. So I consider the theory which is of this. Okay. This theory is not a Gauss-Bonnet gravity. So this will have ghosts. It has tachyons, but I can always choose parameter space for which there is no tax. But for example, the theory has ghosts. Now, this is the equation of motion where these are higher curvature contribution. I can go ahead and solve my Shockwave solutions. Thankfully, you need a graduate student to solve this, and the graduate student solves it and gives you the solution. This is the solutions of a Shockwave solution for this particular theory. And the solution is extremely complicated. As you can see, all these modified Bessel functions and everything comes. You can look at the Shapiro triangle of a probe graviton in this theory. And this theory will have higher derivative equation. Okay. You have to solve these equations and find a reasonable solution. What determines a reasonable solution? So you demand gravitons which are free. They are solutions like plane waves when they are not interacting with the shock. And after interacting also, they become free waves. And then you want to look at the change in the time delay. You want to calculate the time. And this is something you want to. And this is, we calculate this. Rajesh is my PhD student. Hoshe is one of the author of the CEM paper. Alok is also a faculty at India. So we calculated this time delay. Of course, I'm not going to show the calculation. What we found is remarkably that this is of structure GR into 1 minus something. And this something is always less than 1. Okay. So we found at least one theory. The theory has ghosts, but delta V never changes sign. Exactly that of general relativity for any choice of polarization. In fact, this result is independent of the polarization. So this quadratic gravity, let's call the theory quadratic gravity, is free from causality in the sense of CEMZ. But again, it's not a very non-trivial example. Why? Because you can show that quadratic gravity has same 3-point coupling to G. This theory, so go there, okay, there. If you add this term, you can use field redefinition and show this theory has same 3-point coupling to general relativity. So it's not a very non-trivial example because CEMZ has shown that only the Shapiro time delay changes or become sign changes only if you change the 3-point coupling. Okay. So therefore, although it's an interesting example, it's nothing non-trivial. Okay. So therefore, one would look for a theory. So one would like to test this causality constant for a theory of gravity with 3-point coupling different from GR. But let's say it has ghosts. Okay. And you're giving me a lot of leeway for allowing ghosts. I'll explain why ghosts are not that bad as you know. So this is what we call generalized quadratic gravity. So this is of this form, alpha R square, beta RAB plus gamma into some Gauss-Bonnet coupling, which I told about. So if alpha and beta equal to 0, I go back to original CEMZ problem. Okay. And then I will have a problem with the causality. Again, this we call generalized quadratic gravity. This will appear in PRD very soon. So this theory also have an exact Shockwave solution. Again, you need a graduate student to solve this Shockwave solution. It turns out we found a new solution, again some complicated functions come. And in this background, you look at perturbative solution equations for the graviton. Okay. So there is a shock wave of this higher curvature theory. Graviton comes, graviton goes. You want to calculate the change in delta, change in V. Okay. Again, you put boundary condition because you have to have a gauge invariant wave. So you said that you come from plane wave, go to plane wave, and then I calculate what is the change in delta. Okay. So e to the power I V P V and e to the power I P V prime. So then V prime minus V is my change in the time.
Sorry, why the 3-point coupling is so special? Do we have any other, why the 3-point coupling is so special? Do we have any similar constraint from like say higher point coupling?
Excellent. And the answer is we don't know. Except I am going to mention the 4-point coupling. Okay. There is other bound, something called chaos bound. Chaos bound means that in ADS-CFT context, there is a bound which says there are other bounds, something called CRG bounds related to the chaos bound in ADS-CFT. The 4-point coupling and higher order coupling may be relevant to those kind of bounds. But the 3-point coupling is only relevant to classical causality constraint. So we do not know any physical understanding why exactly it happens, but it seems it is what it is. I at least don't have a better physical understanding. I know the higher point couplings may be relevant for CRG bounds and those kind of things, but I don't have a physical way of understanding why it is shown. And it's actually a very important question. Why? And then we found this particular calculation. So this is again some eta is some polarization dependent, and you can show that for all physical polarization, eta is between 0 to half. This is just a normalization. So what we say, okay, Einstein postulated gravity, there is no choice of this coupling which are not order 1. That means you are looking at couplings which are much less than B square. Okay. They are order 1 coupling, not order 1 coupling. And sorry, couplings which are order of B square, because B is classical. The impact parameter is classical for you. You are doing classical scattering. And you can get rid of the negatives. But it turns out, by using the extra degrees of freedom provided by other parameters, we can still choose couplings which are order 1, but delta V is definitely positive for all polarizations. So this is the phase space, where K is some kind of choice of the coupling. So you can show that this is the not allowed part. So eta goes from 0 to 0.5. If you are at 0.1, up to this part, you are not allowed. But so, for example, suppose you choose any eta, if kappa is, this K is 4, for every eta, delta V is positive. So there is a choice, just like the no tachyon condition. There is a choice now opened up in parameter space, for which delta V has a single stop for every choice of parameter. So somehow we can violate this theorem by seeing that. So let me emphasize the importance of this result. This changes the 3-point coupling because there is a LGB. Okay. Nevertheless, there is a parameter space for which the Shapiro time delay can be made positive. And why? In fact, you can show that in higher dimensions also you can do. I'm not going into this choice of that. So why is this happening? Before I go into idea, the main idea is that we are using a ghost. Because remember, I told you that the result in CEM shows that you cannot add a massive particle. And if you add a massive particle, nothing will change. But they assume the particles are not ghosts. Our theory has a spectrum, which is a ghost. Wrong sign on the kinetic term. And it is the ghost which is saving us into this causality problem. So it's very interesting. You have two different problems. Ghost itself is a problem. Causality itself is a problem. If you want no ghost, you will enter into causality problem. If you want causality to go away, you have to have a ghost. Okay. So it's a double-sided sword. Okay. I don't know what there is a Chinese term for it. Okay. I'm sure there will be. Now you may say that is the ghost a bad idea? So I'll give you one example. At least in quadratic gravity, the perturbative ghost may not be a bad idea because you can show that quadratic gravity has a positive mass. There is a result by Gilbert and Tekin. So the perturbation theory if you move around the flat space-time, you get wrong side of the kinetic term. You may think this is instability. But the full non-perturbative positive mass theorem is there. So as a result, maybe the problem in the, by the way, this is only true in quadratic gravity. There is no proof for general higher curvature theory. Okay, so I should be honest. Okay, at least for the general, once you have RABCD term, then you do such proof of positive. So basically, it could happen that what you are looking at, the perturbative ghost, may not be such a bad. But I should also mention a very, very interesting paper by Defion, Alan Hurd, and their group, which is came up, and there are a lot of other interesting follow-up work. What they have shown that at least, for example, if you have this kind of theory, just a toy model, where sigma can be negative. Okay, this is a problem with ghosts, right? They have shown that if you assume integrability potentials which are integratable, a large class of integrable model, they show the phase space motion actually remains bounded for a very large time. Even if there is an instability, negative wrong sign of kinetic term, somehow the phase space never goes away. The particles don't go into the. So what basically the claim is that you should not use your notions of perturbative instability into a non-perturbative regime. Okay. By the way, this is a very specific model dependent analysis. Okay. It's not a general theorem, I must say. Nevertheless, they also showed that, for example, in quadratic gravity, they did the full nonlinear evolution of the binary waveform. And they showed that the evolution remains perfectly well defined up to a very large scale, up to the margin. There is no instability. It's a numerical waveform. You can check. I mean, of course, I cannot reproduce that waveform. But it seems, okay, even if the host, the parameter, somehow the trajectory in the phase space never goes to this probability. I don't understand this result properly. I need to calculate, but it seems that the perturbative ghost may not be bad. But I must emphasize this is only for a very specific model. In general, there is no. So what is the big picture? The big picture is that higher curvature theory possibly makes sense as a standalone classical theory in a CEM, provided the theories will have also perturbative ghost. Okay. The existence of perturbative ghost may not be a problem for a nonlinear theory of gravity. I put my finger crossed. I don't know a general theorem, but there are certain indications. We need further understanding of the theories with ghosts. As I was talking about, there are other bounds. There is a very important bound called CRG bound, Ricci trajectory, classical Ricci trajectory bound. So basically, it says any classical theory whose scattering grows faster than S square at a fixed t, S square and S and T are Mendelssohn variables, is physically unacceptable. In some sense, GR saturates the bound. Okay. So I give you a very simple thing. For example, if your theory has a force mediating particle, let's say spin 3, then you can show the Mendelssohn momentum exchange will be S to the power J, where J is 3. Now we know that higher spin theories, when you have massless particle with spin greater than 2, are in some sense a badly behaved theory because of the Weinberg-Witten theorem. Okay. So this is an example when you go greater than S square, the theories will be bad. The CRG bound is actually motivated by what is called a holographic chaos bound. I mean, very interesting, but there is no, at least I don't know any. See, the CMZ bound has a non-holographic motivation. But CRG bound is entirely, at least I don't know anything independent of holography. But these are very important bounds in understanding the consistent space of solutions beyond general relativity. But there are some indirect evidence that this bound should be valid for every theory in an asymptotically flat background also. These are very preliminary results. This mostly come from, I mean, I can give you the reference. We still don't know what is the relationship between CEMZ and CRG. There is some hand-wavy calculation saying that one implies other, but there are certain analyticity property of the scattering amplitude we have to assume. It will be interesting to know what are these different consistency conditions can we bound. And then, of course, what about theories with ghosts? If I have ghost field, what happens to this thing? See, let me emphasize, I'm not saying the ghost is bad or good. I'm saying it's quite interesting that different consistency conditions, how they play with each other. So I will not go into this kind of, I think I've already overshot my time. So I'll just go to the big picture. The high curvature theories can be constrained using theoretical consistency condition. It seems there is a class of theories which may present well post gravitational dynamics in a sense of causality. There is a parameter space. Okay. But there are very, very important open problems. For example, positive mass theorem. We still don't know what class of high curvature theories allows positive mass theorems or not. And this is an important thing to study. But positive mass, basically, can one generalize Witten's proofs of positive mass theorems into, let's say, 5-dimensional Gauss-Bonnet cavity? It will be very interesting to study fermions. The problem is higher dimensions itself will be a problem. Okay. Because there are issues in how do you study fermions in this. But anyway. Then there are stability of compact objects like black holes in this case are not. And then there's also a very interesting recent work or like rotating black hole solution. So for example, once you go beyond general relativity, Kerr has a very interesting property. For example, you must have noticed if you check T2 minus T and phi 2 minus phi, Kerr remains same. There is what Kerr is axisymmetric solutions also. There is a del phi is a killing vector. Is there a guarantee that all theories, stationary black holes are also axisymmetric? In general relativity, it is guaranteed that what is called the uniqueness theorem. All rotating stationary black holes are axisymmetric in general relativity, at least in asymptotic. Is it guaranteed in other theories? Then if I go beyond axisymmetry, what will be the signature in quasi-normal modes? Can I, for example, does this T2 minus T phi 2 minus phi symmetry always will be there? If it is not there, what will be the signature in TN spectrum or in, let's say, gravitational wave spectrum? These are very, very interesting questions, and our groups have written some papers on this, how to look at the signatures, okay? Because you don't know exact solutions. You see, even deriving Kerr solution is difficult. Even with mathematics, it is not easy, okay? But deriving a generic black hole, rotating black hole solution in a theory which is not general relativity, we have some test solutions using the linearized regime, but full nonlinear solutions we don't have. And therefore, it is important to understand the properties of those solutions. And this is something which a lot of people are doing because it has both theoretical as well as observation consequence. So therefore, with this, I think we should start. Thank you.
Okay, it's a very inspiring talk. So please ask questions.
As you talk about the R squared term in the higher curvature. So what about higher, I mean, much higher curvature terms? So for example, R to the fourth, do you have any intuitively thinking about those terms? Do those terms lead to ghost or modality problem? Like that?
I wish if I can do this calculation. The problem is doing the calculations. Okay.
Yeah.
Even at R square order, we know there are problems with ghosts. So even if you go to higher order term, you will have more problem because the phase space will become more and more multidimensional. So therefore, the problem with ghost, probability ghost will be there in all such space except in Lovelock. So since the problem is already there at R square, I would suggest that let us first understand the R square, then go to the higher curvature, higher and higher curvature. So ideally, I would love to go and study what happens. So there are certain, there is something called this infinite order guarantee, which people have studied. What if you have all possible terms? Is there a non-perturbative completion? Okay, maybe there is a functions of curvature which does not allow you to tell an extent. Okay, possible. I mean,
yeah.
Who knows? Okay. Particularly, these solutions have non-GR branches. Okay. So it's a very interesting question, but you are limited by numerical and computational ability.
Because intuitively speaking, if you are introducing R square term, you will lead to some 3-point vertex in your that is different from GR. But I think maybe R higher, for example, R to the fourth, you will not have that kind of 3-point vertex.
So generally, the expectation is that a problem coming from 3-point coupling
Yes.
will not be annulled or cancelled by something from the higher point contribution, because they will be generally subleading order contribution. That's the expectation, but there are examples from which it happens. In string theory, there are calculations. For example, the famous anomalies and cancellations in string theory, some leading order calculations cancelled by loop cancellation. So maybe that happens, okay, but again, one has to check. That's all.
Yes, yes, I understand. Thank you for your inspiring talk.
Yeah, how about the simpler version that we only have this alpha term, the so-called the Stalovsky model.
Ah,
so
yeah.
alpha.
It's too simple.
Yeah, but what of the problems you mentioned here?
No, because of simple fact that f of r theory is almost similar to GR because of field distribution. You can always, except you have to put a constraint that f prime r to be positive. If you do that, then this theory you can show it is nothing but general relativity with some non-minimal coupling in the potentials. Okay? And since it's a conformal mapping between general relativity and thing, all the causal properties are invariant as long as f prime r is positive. So therefore, there is no problem in f of r gravity. They don't modify the 3-point coupling also. So therefore, that's it. At least in this sense. They don't have even ghost terms as long as f prime r is positive.
That's good.
You mean they have the same 3-point amplitudes?
Can you repeat it?
So you mean accelerate have the same 3-point amplitudes with
Yeah, f of r will have, because what you can show that they can be mapped into GR with. So basically, what happens is that they are equivalent to general relativity with Newton's constant modified by f prime r by g. So if your f prime r has a specific sign, then you are okay. But they may have other problems which I don't know.
And all these constraints are very singular at 4 dimensions, right?
Good point.
Yeah.
So
It seems that we are living in general relativity in 4 dimensions. That will be a very simple job. But I'll tell you, the causality constraint can be constructed in 4 dimensions also. It is a little bit difficult because of these log terms. There will be
Yeah.
IR cutoff.
yes,
So you have to define some standard observer. With respect to that standard observer, you have to calculate this change in V. So that this IR terms, so it's like log IR cutoff by something minus log IR cutoff by something. You have to cancel that IR cutoff in the definition.
Mhm.
So that is a little bit non-trivial, but there is a paper by Ford, I think, okay, where they show how to understand these issues in 4 dimensions. I have to see that. I don't remember the exact name of the paper. It's so
okay.
But the CRG has constraint in 4 dimensions also.
Mhm.
In fact, CRG shows that up to certain dimension, if I remember 6 dimensions or so, I mean, almost everything can be ruled out except curvature, higher curvature gravity, except log gravity. Everything will have a problem with CRG bound. But again, these are theories, first of all, with no host. Okay, they have constructed that host. It's in a perturbative sense, there is no host. And also the CRG bound is motivated by holography. So if you do not believe in holography, then why you do consider CRG bound seriously? But CEMJ bound has rather flat space-time, asymptotically flat space-time interpretation. I think it will be interesting to understand the interplay of this bound, which we do not know.
So is there an artworks to test the C and bound in R multiplication series?
Can you repeat again?
Oh, sorry. So is there any artworks to test the C and bound in R multiplication series?
Is there
Is there any artworks to test the
Is there
C and
Other
bound?
works. So can you test the?
Yeah, so there are one paper in lower dimension, there is a paper by Faucher.
Okay.
In 3D massive gravity, they have looked at this kind of calculations. So apart from that, I would say read my paper.
Any other questions? Do we have any question from online audience? You can speak louder. Okay, okay. If no, let's send the speaker again. Okay.
Take.
Yeah. Yes.